talk about 2D materials for photovoltaic energy harvest.
Hello, everyone. Can you hear me? Okay, so first I would like to thank Danilo and Alexandre for organizing this very nice workshop, and we're very happy to talk to a lot of friends and see what you guys are doing. I will talk about 2D materials for photovoltaics. And I would like to start with these two impressive graphs. So here is the CO2 emission from 2000 to 2018. And you see that it comes mostly for coal, oil, and gas. And when you look at the energy consumption, you say, is the same graph? No, it's very similar. But here's the energy consumption from 2000 to 2018. It's coal, oil, and gas. So of course, if you want to diminish global emission, we need to take care of that. And one of the possibilities, of course, you all know, is increasing renewable energies. We see that it's increasing very fastly, but the challenge is to keep this rate of increasing is not easy, and also to maybe to try to even increase this rate. So it's a big challenge, and we try to maybe help a little bit with that. Of course, here we have several kind of energy productions. One of them is photovoltaics. Photovoltaics is the direct conversion of light to electronic to electro energy. And we need semiconductors because we want to create electron-hole pairs with light. And also we need somehow to separate spatially electron from holes. And two of the main processes are p-n junctions and also type 2 ether structure. There are others. I'll mention a third type in my talk. So we can use several kinds of semiconductors to do photovoltaics. 3-5 semiconductors, mostly tandem 3-5 semiconductors are the most efficient way, but they are very expensive. If you buy a solar system for your home, for your house, probably it will be done from silicon. It's very industry loves silicon, so that's one of the reasons most of commercial available solar systems, solar cell systems are done by silicon. But there are several other kinds of systems. For instance, Marilia and other people talk about organic semiconductors that can be used for photovoltaics. Perovskite is very impressive because the efficiency of perovskite has increased a lot in the last decade, so it's also very important, several other kinds of materials. But more recently, two-dimensional semiconductors has also been proposed to build photovoltaics systems. This is a review from 2018. There are a lot of kind of systems that you can use different 2D materials in photovoltaics. We can have out-of-plane junctions, we can have in-plane junctions, we can have 2D materials with 3D materials. We can have some system where the light interaction only with 2D materials. And here I show the efficiency of 3D solar cells. For instance, gallium arsenide silicon solar cells, they have very high efficiency. But when you look to 2D solar cells, the efficiency still are quite low. And that's because this is a very new field. And that's actually, it's, for me as a scientist, it's interesting because we have a lot to learn about these materials and a lot of suggestions to do in order to improve the efficiency of the 2D materials. This is a new field, as far as I know. Those are the first papers that show the photovoltaic effect with 2D materials. They're from 2014, so it's very, very recent. These three groups showed, and in these three cases, they used this transition metal decalcogenides to do the solar cells. I will show only two more recent experimental examples, only to understand some aspects here. So here they have this system. They have MOS2 and tungstenium diselenide, okay? And they have a glass substrate. Why they have glass here? Because they want a transparent solar cell. And that's very amazing for me when I first saw this paper, because they have a system that is 80% transparent and yet has 10% solar cell efficiency. So it's impressive. I would like to pay attention that this is not a monolayer, a few layers. This is several layers. No? Here they have thickness between 4 to 20 nanometers. So they have like something between 7 to 11 layers. Why? Because if you have just one layer, of course, the light absorption will be very bad. So you need to have a few layers, not so few, several layers, in order to build this kind of efficiency. Here is also in black. You have, with no light, you don't see almost nothing when you plot, when you measure current against voltage, but with light, the photovoltaics effect clearly appears, okay? Another example that I would show to you is flexible solar cells. So here they have, so here's is different, because here they don't have a type 2 ether structure. Here they actually have a semiconductor and a metal. They have graphene. So this is a Schottky barrier. So they use the Schottky barrier to separate electrons on hole in this kind of system. So it's another kind of materials, and they can have a flexible solar cells. So the efficiency is not so large, but anyhow, it's another possibility. So we can have transparent solar cells, and also we can have flexible solar cells with the use two-dimensional materials. Something that I would call the attention is the importance of excitons in this kind of semiconductors. Why? Because when you have a two-dimensional material, we have enhanced Coulomb interactions. This comes from the weak dielectric screening, and also because of the quantum confinement of the charge in two-dimensional. So for instance, in 3D gallium arsenide, the binding energy of excitons is just 4 millieV. However, in monolayer tungstenium disulfide or in few layers black phosphorus, this can be two orders of magnitude larger. So that is excitons in 2D semiconductors. They are very, very important, and this is something that we need to take in account in order to understand the light absorption, of course. So here is an example for molybdenum disulfide of the importance of excitons. So they measured the absorption of light with as a function of energy. So those are the two excitons that appear in molybdenum disulfide. This is for 5K, but when you go to room temperature, you still see the excitons, because the binding energy is quite large. And when you go to few layers, I said to you that if you want to build photovoltaic devices with 2D materials, we won't have, we probably won't use just monolayers. We need several layers, multi-layer materials, and then it's interesting to see what happens. And for our surprise, for several layers in this kind of materials, there are several things that are yet not very well understood. For instance, people still discuss the origin of the excitons. Where in the Brillouin zone are the excitons is one of the things that's not totally understood also. And also the presence of interlayer excitons, where the electron and hole are not in the same layer. So this is very interesting. That has several applications, and is not yet not completely understood. Even for molybdenum, probably molybdenum disulfide is probably the most studied 2D semiconductor. It has been in the last decade very, very well studied, but even in these systems, when you go to several layers or bulk, there are several things that are not well understood. So what we are trying to do, I will show some very preliminary results. What I try to do is to understand optoelectronic and vibrational properties of 2D semiconductors. Vibrational properties are very important because the electron hole can recombinate for several mechanisms. One of them is, of course, electron phonon coupling. We focus on PV and other energy-related applications. And excitons are crucial if you want to understand this kind of systems. And we are mostly interested in how these properties depends with thickness. So because multi-layered materials are important in this case. One thing that we need to know is how can we estimate the efficiency of some kind of material for solar cells. This was done, there is this paper from the 60s from Shockley and Quasiparticle. And what they did, they just use the detailed balance, and they have a very interesting result that they say the efficiency depends of the band gap in this way here. But here they only take in account the band gap. And what you can say is that you need to have band gaps in the order of 1 to 1.5 EV if you want to have good efficiency. However, now Liping Yu and Alexander propose a more sophisticated way to calculate the efficiency, where they take in account not just the band gap, but also the thickness, because we can calculate the absorption coefficient if you know the dielectric constant, and then the absorptivity can be in this very simple model. It will depend, of course, in the thickness, okay? And also, in the case of Shockley and Quasiparticle, they don't take into account the shape of the absorbed. They just take the absorbed is 1 if the energy is larger than the band gap, and 0 otherwise. But here we can calculate the absorbed, and then we can take into account the shape of absorption spectra. And also, they have a very simple model for the relative importance of radiative and non-radiative recombination loss. Okay, so they did this for this kind of material, and here, for instance, you see that there is a big difference. The efficiency depends on the thickness of the material. You see that these two are very efficient. This one is not very efficient. That's because of the band gap. These two have direct band gap. This one has indirect band gaps. That's the main reason. So if you go to this thickness, 400 nanometers, for instance, and if we look for silicon and gallium arsenide, the efficiency of silicon is only 6% for this thickness. That's why we need, in silicon solar cells, we need almost 1 millimeter thickness. It's 500 micrometers, the solar cells from silicon, to get the efficiency that is needed for energy production. And gallium arsenide here would be almost 30%. So just to give you the numbers for two very well-known semiconductors. So here they show the Shockley-Quasar limit and also the efficiency calculated by their approach. What we did, we start to look for this kind of transition metal decalcogenide because they are very well studied, and there are several experimental implementations of photovoltaic device for them. And we look at the bulk phase. I mean, we looked for an infinite number of layers because we think that in the actual devices, when you have like something like 10 or 20 layers, the properties are very close already of the bulk phase, of the infinite number of layers. We did DFT calculations, and then we, on top of that, we use many-body perturbation theory because we need to have a very good description of the gap and also of the electronic structure. So it's very important to have some kind of something beyond just a local or semi-local DFT, and we did GW. And because of the importance of the excitons, we also solved the Betz-Salpeter equations to get the properties of excitons. This is the crystal structure. We use the 2-8 phase, which is the most stable phase for these bulky materials. We have a good results for the structure as expected. Here is something very interesting that we are still trying to understand better, is that when you look of, this is MEOS2 with and without spin orbit coupling in the calculations. And the band looks very similar in the two kind of calculations. In this graph, they look exactly the same. However, when we calculate the dielectric constant, they are not so similar. So somehow, we still don't understand very well, but somehow, even though the energy in the bands are not so different, the oscillator strength changes a lot when we include spin orbit coupling. So that's something interesting. So even in this, we need to include also in our calculation spin orbit coupling to have a good description of the absorption. Here we have for the four materials the bands calculated with PBE. The dashed lines are PBE, and the solid lines are the GW calculation. So as expected, with GW we have a larger and more accurate band gaps, but also you see that it's almost a rigid shift, but it's not exactly a rigid shift. So there is some difference in the electronic structure when you shift. We do the many-body perturbation calculations. So here we have the band gap. So if we compare the PBE results with the experiment as expected, the results are very wrong. In general, they are very much smaller than experimental results. However, as expected also, for the GW calculations, we get a much better agreement of our calculations and experiments. And here we compare our Betz-Salpeter optical absorption. So here already we include the excitons, and we compare with the experimental absorption. So we see that these excitons peaks that people, the experimentalists see in their results, we can reproduce then with a very good accuracy. And here I show to you the binding energy of the excitons. So we see that the binding energy of the exciton are in the order of several tenths of millielectron volts. So they are not so large as when you compare with the monolayers. In monolayers, the exciton binding energies are very, very large, but they're not small also. They are much larger than the thermal energy at room temperature, for instance. So much larger than one, but larger than the thermal energy at room temperature. And we have a very good agreement with experimentals. So that's interesting because that shows that the question of the binding energy of excitons being large in this kind of materials is not only due to the electron screening, but also to quantum confinement. Because here we have bulk materials, I mean, infinite number of layers. So a very large number of layers, I mean. So that's also interesting. And here we have actually the results of current in function of voltage and power in function of voltage, and the efficiency of the photovoltaic systems calculated using the U and Zunger method as a function of thickness. So for instance, if you look here, I think that the most interesting is look to this plot for small thickness. For instance, here is 20 nanometers. So for 20 nanometers, we see that we can have efficiency in the order of 5 until almost 15%. So we can have, with this kind of materials, very good efficiency, especially if you look at these two here, is tungsten diselenide, and this one is molybdenum diselenide. So especially for the diselenide, we can have a very good efficiency, considering if you consider how thin are these systems. So here in general, people use it's a convention in the field. People use 500 nanometers to compare different materials, and for 400 nanometers, we have this kind of efficiency in the order of 13 to 19%. Remember that, for instance, gallium arsenide, that's known to have a very, very good efficiency. This number is 30%. So we can, of course, this kind of materials, the idea is not compete with silicon or gallium arsenide. That's not the point. The point is find some niches in the market, for instance, in transparent solar cells or flexible solar cells, and this kind of materials can be interesting. So here is the example of gallium arsenide. Concluding, I showed that spin-orbit coupling is crucial in this kind of description that you want to do. Money-Berry perturbation and Betz-Salpeter calculations give very good results for electronic structure, optical absorptions, and exciton binding energy. And the efficiency of these materials for photovoltaic effect is good, especially for the diselenides. Now we are finishing the work of the exciton wave functions in order to see the actual properties of these excitons, where they come from in the Brillouin zone, if there are or not interlayer excitons. This is a work in progress. This work was done in collaboration with Enesio from here, Cesar from Peru, and Alexandre. And I would like to thank the these institutions here. And I would like to finish with a very beautiful photo. This is actually a photo that was taken from inside our building in the Physics Institute in Niterói. So many of you know our campus. For you that don't know, you are invited to come and visit our campus. Thank you very much for your attention.
And you're from São Paulo, right, Pedro?
I'm from Santo André.
Santo André. Okay, are there questions?
Very nice talk. I have two questions already. First one, this is, you're piling up layers, is that so? It's infinite. So you don't use van der Waals interactions?
No, we do use. Yeah.
Okay, so it's just not written there.
Yeah, I forgot. Yeah.
Oh, okay,
yeah.
okay.
Very good. Thank you for reminding.
Okay. The second one, do you have the reason how the spin orbit has such a dramatic effect in that?
We didn't understand yet, but somehow the spin orbit is changing the oscillator strength. So it's just change the question. So do you know why this changes? We are trying to understand, but not yet.
Valley?
Sorry.
Do they have some valley changing and then change the occupation from one spin to the other through different valleys, maybe?
I don't know, because if you look at the band, you see the same band, but you mean?
Yeah, you don't have any valley. Yeah. You have a valley in the middle there.
Yeah.
But maybe, okay. Okay, thank you.
Hey, Pedro, thank you for the great talk. So I have also two quick questions. The first one, when you show the shift in the band structure with G, it seems exactly what you said. It's just a rigid shift. But did you check if there is some change in the effective mass, even if it's small when you apply GW? And the second question is actually not very clear to me if exciton helps or difficult, like if it improves or not the efficiency of a solar cell based on 2D materials. Because in principle, it seems that a strong exciton binding energy would be more difficult to create electron-hole pairs and then generate electricity. But on the other hand, there are also those excitonic solar cells that I'm not sure exactly how it works. So could you comment a bit on that as well? Thank you.
Okay, so we didn't calculate the effective masses, but if you look more careful in the shape here, we see that there are some small difference. So it's not just a rigid shift. It's in a first approximation, we can maybe see that as a rigid shift, but it's not exactly. So there are some difference, but we didn't actually calculate the effective mass to look at that. Maybe it's a good idea. How the other question is how the excitons influence in the efficiency. So let me, here I have in this plot we see the spectral irradiance of the sunlight in the Earth in Earth. So that's the light, the sunlight that arrives to us. So we see that it's large in this region, from 1 to maybe 2 eV. So what can happen is that if you here now. So when you create excitons in these regions, and this is the case here and here, you increase the absorption. So in this sense, excitons are crucial for the efficient cells, because you can have semiconductors with a large band gap. However, you can introduce excitons exactly where the most of sunlight are. So that's how important can be excitons in this kind of systems.
Questions? If not, let's thank Pedro again.